Here I'm going to be looking at calculus, in particular differentiation by first principles. I've just put up the image on the right there just to show that this is where I want to get to after explaining a few things about rates of change and points on a Cartesian plane and things like that. Okay, so that's where I want to get to in the end. So to start with, let's just talk about calculus and differentiation. Calculus allows you to measure the change in one thing with respect to another. Okay, and if you think back to coordinate geometry, especially coordinate geometry, the line, we know that we can find the rate of change of one value with respect to another by finding the relationship between them, i.e. the slope between one point and another point. So we're looking at a rate of change here. The slope of any line, m, was equal to the difference between the y values, that was y2 minus y1, over the difference between the x values, x2 minus x1. So what I'm going to plot now is just 2 points, A and B, on my Cartesian plane or on the graph here. Call that A, and I'm going to call this point B. So the rate of change for that line is always the same because it's a straight line. So the slope of that line, which is the rate of change, is just the difference in the y values divided by the difference in the x values. Now that's fairly straightforward for a straight line because the slope is always the same at any point on that straight line, provided that the line is a straight line. So if it's not a straight line, that means the line is changing direction on going from point to point, and so the slope is not constant. So let's have a look at a situation where we don't have a straight line. So I've drawn in my red curve, which has the points A and B. Now, if I wanted to work out the average rate of change, I go from A to B on my red line, that would just be the slope of the line I go from A to B, which is the difference in the y values divided by the difference in the x values, which is the formula that I've got down below here. So that gives me the slope of the line AB, which is the average rate of change I'm going from A to B. What I'm going to do now is going to try and come up with a formula that allows us to work out the slope at any point on that curve, which is actually differentiation by first principles. Differentiation is just the rate of change. So it's the rate of change of y with respect to the rate of change of x. Okay, so what I'm going to do is I'm going to give my points A and B some coordinates. So the x value of A I'm just going to call x, and the y value of A I'm just going to call f of x. So that is just going to be f of x. Now I'm going to say that what's happened to B in terms of its x value is it's moved up by some distance h. So the x value of B is just the x value of A, which is x, plus some number h. That just means that all I've done is I've increased the x value by some distance h. Okay, so I've called the x value of B x plus h. Well, what does that make the y value of B? Well, if the y value of A was just f of x, i.e. put x through the particular function, then the y value of B is just f of x plus h. So I've got my coordinates. The coordinates of A is f of x and f of x. So A just becomes the point x, f of x, and B just becomes the point x plus h and f of x plus h. So just a very generic term there. So here m becomes, just going to switch to blue writing for this, m becomes the difference between the y's, so the y value of B, which was this one, f of x plus h, minus the y value of A, which is just f of x, all divided by the x value of B, which is just x plus h, minus the x value of A, which is x. And so I'm just going to tidy that up. That just equals to f of x plus h minus f of x, all divided by x plus h minus x, which is just h. So to work out the average slope of that line, we just take the y values and subtract them and divide by the difference between the x values, which was just h, because that's what we implemented. Now we're very close to finishing this, because I purposefully left this as some generic case h, because h could be a variable, i.e. as I moved up from my curve from x all the way to this value, I've moved all the way along this curve just by simply increasing the x by some h. Well, let's say I wanted to work out the slope at the point A on the curve, exactly at the point A. Well, I would just take its y values and subtract them, and take its x values and subtract them. But if I was taking its x values and subtract them at the point A, the x values are the same, so I would get 0 as the denominator. I'd also get 0 as the numerator because the y values would be the same, so this would be the indeterminate form that I looked at briefly in the limits video. So really, to work out the slope at any point, I just simply take the point and move it a certain distance h. But if I wanted to actually work out the slope at any point, I wouldn't want to move it at all. So I'd want that value h to be as close to 0 as possible, but without being actually 0. So the limit as h goes to 0 was really what I'm looking for, because if I want the slope at A, I need the point infinitely close to A without being A, which is essentially just taking its x value and moving it as close as possible to 0 without it being 0, which is the limit as h goes to 0. So technically, to find the slope at any point along the curve, what I want to do here is I want to take the limit as h goes to 0 of f of x plus h minus f of x all over h. So what this formula allows me to do is work out the slope at any point along the graph. So I'm just going to go through a past paper question on this now. So I should say before I do that, a bit of terminology. When we're looking to find the slope at any point, we just call, and we've written the function of f of x, then f prime of x is the derivative, or the first derivative, and that's what that is equal to. It's also, if we write the function as y equals to some function, then we write the derivative of that function dy over dx, where that's the change in y, delta y, over the change in x, delta x. We can think of it in that way. So let's have a look at this past paper question on differentiation by first principles. It says to differentiate the function 2x squared minus 3x minus 6 with respect to x from first principles. This came up in 2014. Well, I know where I need to get to. I need to get to this point here. So let's look at it. I know that f of x is equal to 2x squared minus 3x minus 6. So I want to work out what does f of x plus h equal to. That is going to be 2x plus h, all to be squared. We just simply substitute x plus h in for x, minus 3 times x plus h minus 6. So now what I'm going to do is I'm going to expand the brackets, because I'm going to end up subtracting those two from each other. That's going to be 2 outside of x squared plus 2xh plus h squared. Remember, when we're expanding a squared term, it's going to be the first by itself plus twice first by the second plus the second by itself, minus 3x minus 3h minus 6. And just to expand this out, 2x squared plus 4xh plus 2h squared minus 3x minus 3h minus 6. Okay, so there's quite a lot of terms there, but that is what f of x plus h expanded out is equal to. What I'm asked to do next is to subtract them. So f of x plus h minus f of x is equal to this part minus this part. So that's just going to be 2x squared plus 4xh plus 2h squared minus 3x minus 3h minus 6, and we're subtracting the original function, which is 2x squared minus 3x minus 6. So that leaves us with 2x squared minus 2x squared. We've got 4xh plus 2h squared. You've got minus 3x minus minus 3x, which is plus 3x, so they cancel out. You've then got minus 3h, and you've got minus 6 minus minus 6, so that goes. So what happens is the original function just cancels out. So we're just left with 4xh plus 2h squared minus 3h. Then if we quickly look what we're asked to do next, we have to divide all of that by h. So f of x plus h minus f of x all divided by h is equal to 4xh plus 2h squared minus 3h all divided by h, and that is just equal to 4x plus 2h minus 3. The last thing I'm asked to do, if we look back, is to find the limit as h goes to 0. So the limit of this as h goes to 0 is lim h goes to 0 of f of x plus h minus f of x all over h. As h goes to 0, well, when we're working out a limit as h goes to 0 for a standard function like this, we just simply plug in 0 for h. So that is just equal to 4x minus 3. So f prime of x is simply equal to 4x minus 3. What that means is, to find the slope at any point along that curve, we simply plug in the x value into 4x minus 3 and we get the slope. So if the function looks something like this, all I would need to do is plug in any value of x, and what the derivative allows me to do is it works out the slope at that point on the curve. So for example, in this particular question, it's not asking me to do it, but just to show you, the slope at x is equal to 3 would be 4 times 3 minus 3, which is 9. So I'm not surprised that on this particular function, the slope, when x is 3, we've got quite a steep line like that, because it's a positive gradient. The slope at x is equal to 0, we have 4 times 0 minus 3, which is just minus 3. So I'm not surprised then that when x is 0, I've got a negative slope. That means as x increases, y is decreasing. Okay, so that's what calculus allows us to do. It allows us to find the slope of any curve by simply plugging in the x value. Now there's more things that I'm going to show you in the next couple of videos about how to derive functions. There's a far easier method to derive the functions using a particular rule, which I'm going to show you in a following video, but that is an introduction to calculus using first principles.